morning students. So, in the last class I explained about series LCR circuit and I derived the formula for impedance of the circuit. What is the meaning of impedance? It is the total opposition offered by the circuit for the flow of AC. It is due to both resistance and reactance part. Now, we take glance of that discussion. So, series LCR circuit. It is resistance, inductance and capacitor. R, L and C. Now, through all of them current must be same. Let us say peak current is I naught, because we want to draw the phasor diagram by taking peak values. Whenever peak current flows, voltage across the resistor is VR, it is the peak voltage, and VL peak voltage across inductor, VC peak voltage across capacitor. And what is the formula for VR? I naught into R. What is the formula for VL? I naught into XL, and VC equal to I naught into XC, where XL and XC are the inductive and capacitive reactances. Now, see here the phasor drawing is like this. This is I naught. We make simple drawing I naught, and in the same direction we have got VR. Then with respect to I naught, VL is leading by 90 degree and voltage across capacitor is lagging with respect to current, that is VC. So, this is the simple phasor drawing. This is now origin, this is A, B and C. Now, see here voltage across resistor and current through the resistor are in phase. With respect to inductor, voltage leads by 90 degree with respect to current. In the case of capacitor, voltage lags the current by 90 degree. So, this is the simple phasor drawing. And in earlier discussion, we intentionally took VL greater than VC. With this idea, we continued the derivation. If VL is greater than VC, then let us say OD represents VL minus VC. Now, how to find out resultant of VL minus VC and VR? It is the vector sum, because it is the phasor drawing. So, we complete parallelogram, draw the diagonal. So, this is V naught. I will write I naught here. Now, if you take this right angle triangle, then we can write V naught square is equal to, it is VR square plus this side Pythagoras theorem, VL minus VC whole square. Or if you substitute, this is I naught square, sorry 1 minute, it is V naught square is equal to, this is I naught square R square plus I naught XL minus I naught XC whole square. Which term is common? I naught square. Therefore, it is V naught square is equal to, it is I naught square can be taken outside, common term. Then remaining term we can write like this, R square plus XL minus XC the whole square. Or take square root, it is V naught is equal to I naught into square root of R square plus XL minus XC whole square. This can be compared with Ohm's law, that is V equal to I R, just comparison. If you compare V naught, here it is V, so same type of terms, here current, here also current, and here resistance is there. In that position you have got a term square root of R square plus XL minus XC whole square. Therefore, the term inside the square root represents total opposition of the LCR circuit for the flow of AC. It includes resistance part and reactance part. It is now known as impedance. Therefore, it is written as V naught is equal to I naught into Z, where Z is the impedance of the LCR circuit. And by comparison, Z is equal to, it is root of R square plus XL minus XC whole square. So, this much I explained in the last class. Now, we continue this one because these points are very important. We can expect for 5 marks. Now, from this phasor drawing, it is very clear voltage leads the current because voltage is here, it has got a higher phase angle compared to current, and phi is taken as phase difference between voltage and current, and in this case V leads I by an angle phi. And how to find out phi? Tan phi. Tan phi is equal to opposite side. What is the opposite side? VL minus VC divided by adjacent side VR. That is I naught into XL minus I naught into XC divided by I naught into R. I naught is a common term, we can cancel. So, it is tan phi is equal to XL minus XC by R. This is the formula for phase difference between current and voltage. If you simplify this one, we get phi. Phi is equal to tan inverse of XL minus XC by R. Now, what is the interesting point here? See, in the beginning I said VL is greater than VC, or it is written like this, I naught into XL is greater than I naught into XC. I naught we can cancel, XL is greater than XC. So, in this particular circuit, inductive reactance is greater than capacitive reactance. Therefore, in the circuit, inductor property dominates, capacitor property is suppressed. Remember, inductor will control the circuit because its reactance is more, opposition is more. What is the property of inductor? The property of the inductor is that voltage leads the current. Remember, so whenever inductor property dominates in that circuit, definitely voltage leads the current. V leads I. And this is the formula for phase difference. Now, the question comes, in all the circuit, for all the frequencies, whether VL is always greater than VC? No, even VC may be more than VL. This voltage may be higher value, this voltage may be smaller value. For example, VC, let us say 10 volts, this may be 4 volts, VL. Then what is the formula for Z? Very clear. If VC is more than VL, then automatically this parallelogram, in this case it is rectangle, that comes down. So, briefly we see that one by taking another possibility. Now, the phasor drawing like this. This is I naught. In the same direction, we get voltage across resistor. This is VL, and This is voltage across capacitor. Look into this drawing. It is very clear, Vc is more than Vl. So, Vc is greater than Vl. Let us say this is 10 volts, it is 4 volts. What is the resultant? 6 volts. In which direction? Downward. Therefore, we get the resultant of Vl and Vc in the downward direction, like this. So, this represents Vc minus Vl. Now, we complete parallelogram, means in this case it is a rectangle, and this is the applied voltage V naught. So, as usual you apply Pythagoras theorem, and here we get Vc minus Vl. Therefore, if we apply Pythagoras theorem, it is V naught square is equal to Vr square plus, what is this? Vc minus Vl whole square, or it is I naught square R square I naught xc minus I naught xl whole square. And if you continue this one, finally it is V is equal to I naught, V naught is equal to I naught into square root of R square plus xc minus xl whole square. This is the formula for impedance. It is written as now I naught into Z. I naught into Z. What is Z now? Z is equal to square root of R square plus xc minus xl whole square. Earlier xl minus xc, now xc minus xl, that is the difference, and this is the phasor drawing. Now, look here in this phasor drawing, this is current, it is voltage. Who is leading? Current is leading the voltage, and phase difference is phi. So, very clear, current has got a larger phase angle compared to voltage. Therefore, we can say current leads voltage, I leads V by an angle phi. How to find out tan phi? Tan phi is equal to opposite side. What is the opposite side? Vc minus Vl by Vr, that is I naught into xc minus I naught into xl divided by I naught into r. So, I naught we can cancel, phi is equal to tan inverse of xc minus xl by r. Now, again you come back here, Vc greater than Vl, this is the condition, implies that I naught into xc greater than I naught into xl. I naught we can cancel, capacitive reactance is greater than inductive reactance. Look here, in this case, which reactance is more? Capacitive reactance is greater than inductive reactance. Circuit is governed by capacitor. Capacitor property dominates. What is the property of capacitor? The property of the capacitor is I leads V, remember, that is the property. Therefore, we can say in any circuit, if a capacitor reactance is more than inductive reactance, definitely we can say I leads V. So, once you find out capacitor reactance and inductive reactance, we will get the behavior of the LCR circuit, whether current leads or voltage leads. But before that you find out inductive reactance and capacitor reactance. Now, we consider one more possibility. What is the another possibility? In the first case, I said VL greater than VC, over. Second step, I took VC greater than VL, that is this discussion. And the third possibility that they are equal. Think that this is 10 volts and VC is also 10 volts. Just think, if this is 10 volts, it is 10 volts, they cancel each other. Therefore, what is the value of VC minus VL? 0. Means this phasor or this vector, its value becomes 0. If this value becomes 0, then this rectangle collapses. Rectangle collapse agutte. This side becomes 0. This side illa. Idu 0 agutte. V naught, is it not falling on VR? This phasor falls on VR. Means this drawing becomes like this, I naught. In the same direction, we get VR, and in the same direction, you got V naught. So, all three of them are together, and look here, current and voltage are together, they have got the same phase angle. It is nothing but it happens in a resistor circuit. In the last class I explained, in the case of resistor, current and voltage are in phase, they have got the same phase angle, phase difference is 0. Therefore, here current and voltage are together, it is nothing but it acts as a resistor circuit. LCR circuit, even though it is the LCR circuit, now it acts as a resistor circuit, and this phasor drawing becomes like this. Now, whenever this is happening, we say LCR circuit is at electric resonance. There is a good condition for, good explanation for that, why it is known as electric resonance. But whenever this happens, we say LCR circuit is at electric resonance, and you can expect this one for 3 marks in annual exam. What is meant by electric resonance? Obtain the condition or obtain the expression for resonant frequency. I already said, if voltage across inductor and voltage across capacitor, if they are equal, they cancel each other in phasor drawing. Voltage across the circuit V naught, peak value, becomes VR. Now, what is the speciality of electric resonance under that condition? We start with the expression for impedance. Let us say Z is given by square root of R square plus XL minus XC whole square. Let us say it is the equation. Now, you may ask whether you want to take XL minus XC. No, you can take XC minus XL, no problem, because see, this is the difference between the two values, square is always positive. Therefore, whether you write XL minus XC or XC minus XL, you get the same answer and no mark will be deducted. ಹಾಗಾಗಿ ಈ ಪಾಠ ನೀವು ಹೇಗೆ ಬೇಕಾದರೂ ಬರೆಯಬಹುದು. Now, look here. For the given LCR circuit, I want to make impedance minimum. I want to make Z minimum. Under what condition Z becomes a minimum? That is the question. Z becomes a minimum only when this second term is 0. Reactance term must be 0. The reason is, whether it is a positive or negative, square is always positive, it is added to R square. Therefore, Z becomes a minimum only when second term is 0. This cannot be 0 because it is resistance of the circuit. It has got a finite value. Therefore, this, if this is 0, Z is minimum. So, if XL minus XC is equal to 0, then Z is minimum. Okay. That is Z minimum is equal to square root of R square plus 0 square, that is R. Circuit act as a resistance circuit, because see here, impedance is equal to resistance of the LCR circuit. Okay. Now, under what condition this term becomes 0? Listen, under what condition this term becomes 0? This term becomes 0 only for the particular frequency of the applied AC, that is known as resonant frequency. It is not happening for all the frequency of AC, no. It is true, this condition holds good for only one frequency of AC known as resonant frequency. So, that resonant frequency is written as F naught. So, I will write like this: if F is equal to F naught resonant frequency, then XL minus XC is equal to 0. So, substitute what is XL? 2 pi FL, but frequency is the selected frequency F naught is equal to XC, capacitor reactance, 1 divided by 2 pi FC. Again F is equal to what? F naught. Now, simplify this one. F naught square, F naught into F naught square is equal to 1 divided by 2 pi into 2 pi, 4 pi square, LC taken to denominator, or F naught resonant frequency is equal to, it is 1 divided by square root of the denominator 2 pi root LC. Very, very important equation from the point of exam. You can expect even for 1 mark. Write the expression for resonant frequency of LCR circuit. Okay. Now, why we use the term resonance, electric resonance? That also I want to explain. Okay. Now, the reason is like this. Earlier we know that V naught is equal to I naught into Z, or I naught is equal to V naught by Z. At resonance, Z is equal to what? Z minimum. What is Z minimum? R. Implies that I naught is equal to V naught by Z minimum, that is V naught by R. But look here, whenever impedance becomes minimum equal to resistance, then definitely current will be maximum. Current becomes what? Maximum. Therefore, this is the peak value of the current. Peak value of the current becomes maximum. Got it? So, under resonance, impedance of the circuit is minimum, thereby current in the circuit becomes maximum. You have got a highest current in the circuit. Hence, it is known as electric resonance. The reason is, in first PU studied about resonance. What is resonance? The frequency of one system matches with the frequency of another system, then the second system will vibrate with the maximum amplitude that you studied. Got it? So, frequency of one system is equal to frequency of another system, the second system vibrates with the maximum amplitude. Like that, here in this AC circuit, frequency of the AC source is equal to frequency of the LCR circuit, resonant frequency of the LCR circuit. You are adjusting the frequency of the AC source to this frequency. This is the frequency of the LCR circuit. Then current becomes a maximum. Current becomes maximum, therefore, it is known as electric resonance. So, all this discussion you can expect for 3 marks in annual exam. Now, we think of power factor of the circuit. Power factor, that is also important. Power factor already we know it acts as a resistor circuit. Therefore, what about power factor? Power factor must be 1. So, power factor at resonance. Power factor is equal to cos phi is always given by R by Z, or in this case it is R. What is Z? Z is Z minimum is equal to R, that is 1. Therefore, power factor of the circuit is 1. It again indicates that LCR circuit, it behaves or act like a resistor circuit. Now, next one is variation of current with the frequency, that is behavior of the LCR circuit with the frequency of applied AC. So, this we discuss. Now, the discussion is very interesting and very basic. Now, let us say it is the frequency. We take the graph, and in this graph along x axis we take frequency, along y axis we plot both XL and XC, both XL and XC. Now, we know inductive reactance. What is the equation? Inductive reactance 2 pi Fn or XL proportional to frequency. Therefore, if you increase the frequency of the AC, then the inductive reactance increases. Graph is a straight line. Capacitive reactance 1 divided by 2 pi Fc or Xc inversely proportional to frequency. As the frequency of AC increases, capacitive reactance decreases and the graph is exponentially like this, decreasing. It is the graph for capacitor reactance. Now, what is interesting point here? Look at the point of intersection of both the graphs, both the curves. So, here it is very clear. It is XL is equal to XC. Inductive reactance is equal to capacitive reactance, and we know if these two reactances are equal, what is the corresponding frequency? It is resonant frequency. It is what? Resonant frequency. Now, we take any frequency less than resonant frequency, somewhere here between these two. You take any frequency, ಯಾವ frequency ಆಗುತ್ತೆ ತಗೊಳ್ಳಿ. You take the frequency as F1 and you draw vertical line. Draw the vertical line. So, very clear, for this particular frequency, look here, this is the value of capacitive reactance. And what about here? This is the value of inductive reactance. It is representing XC, this becomes XL. So, tell me which value is higher? Capacitive reactance is higher than inductive reactance. And is it true for all the frequencies less than resonant frequency? If you increase the frequency, no doubt, but throughout here capacitive reactance is more, inductive reactance is less. Therefore, who will govern the circuit? Capacitor will govern the circuit, its property dominates. What is the property of the capacitor? In the case of capacitor, current leads the voltage. Therefore, in this range, definitely we can say capacitive reactance is greater than inductive reactance, implies that what is the conclusion? Capacitor controls the circuit. What is the property of capacitor? In the case of capacitor, I leads V. I leads V. What is the equation for impedance? We can write the equation for impedance like this: Z is equal to square root of R square plus it is XC minus XL whole square. Capacitor reactance minus inductive reactance whole square. You can write XL minus XC because the difference is always there and its square is always positive. ಹಾಗಾಗಿ ಇಲ್ಲಿ XL minus XC ಬರೆದರೆ ತಪ್ಪಲ್ಲ, ಆನ್ಸರ್ ಬರುತ್ತೆ. But it is better to write XC minus XL whole square. And what is the equation for phi? Phi is equal to, we can write tan inverse of, it is XC minus XL by R. Okay. Now here we plot another graph. ಇಂಥದ್ದು ಇನ್ನೊಂದು ಗ್ರಾಫ್ ಅನ್ನು ಮಾಡುವ ಇಲ್ಲಿ. This is frequency and here definitely it is resonant frequency, and here along the y axis I am taking current. That current is peak value, okay, I naught. Instead of I naught, even you can plot IRMS, no problem. ಇಲ್ಲಿ IRMS ತಗೋಬಹುದು. Shape of the graph will be same, but throughout the discussion we are taking peak value, therefore I am plotting I naught. Okay. Now see here, you are increasing the frequency of the AC source, means what I say, I am approaching the resonant frequency. Now resonant frequency approach ಆಗ್ತೇನೆ. Gradually I am increasing the resonant frequency, frequency towards resonant frequency. Then what is happening? As you increase the frequency, difference between XL and XC goes on decreases, that is this. Look here, this is actually representing XL minus XC. That difference goes on decreases. As the difference decreases, look here in this formula, this difference value goes on decreases. As the difference value decreases, Z value decreases. As the Z value decreases, current in the circuit increases. Therefore, as you approach the resonant frequency, current in the circuit goes on increases, and here what is the difference? 0. That is resonance. Current is highest. Therefore, graph will be like this. Current is highest at resonance. Now you take any frequency beyond resonant frequency like this. F2. For the frequency F2, which value is more? This is XL. This is which value? XC. So who is which value is greater? Inductive reactance is greater than capacitive reactance. Okay. So it is very clear. Now circuit is governed by inductor. Circuit is governed by inductor, and what is the property of the inductor? V leads I. Therefore, in this range, E range nalli, it is very clear XL greater than XC. Inductor property dominates. What is the property of the inductor? V leads I. Okay. Then what is the equation for Z? Z can be written like this: R square square root of r square plus xl minus xe whole square, and phase difference is given by the formula tan inverse of xl minus xe by r. And moreover, in this graph, this represents xl minus xe, this part xl minus xe, and as frequency increases, difference also increases. This difference becomes more and more. Look here. As the difference increases, reactance part increases. As reactance part increases, Z increases. As Z increases, current in the circuit decreases. Therefore, with the frequency, current decreases. Like this. So, it is the shape of the graph. So, it is known as variation of current with the frequency for the LCR circuit. So, up to resonant frequency, current goes on, increases, and beyond resonant frequency, again current goes on, decreases. And this, you remember this graph even for competitive exam, because thereby you come to know how to write the formula, or which quantity is leading, which quantity is lagging, and if frequency is less than resonant frequency, what is happening to the circuit? If frequency is more than resonant frequency, what about the circuit? And at resonant frequency, what is happening? Now, we discuss another important aspect, that is known as quality factor of the LCR circuit or sharpness of the LCR circuit. Quality factor. Quality factor of the circuit or sharpness of the LCR circuit. Quality factor also written as Q factor. ಹಾಗಾಗಿ quality factor ಹೇಳಬಹುದು Q factor, capital Q, don't write small q. And be careful, quality Q factor, Q ಅಂದರೆ charge ಅಲ್ಲ, it is not the symbol for charge here. So, exam ಅಲ್ಲಿ Q factor ಬರಬಹುದು, quality factor ಬರಬಹುದು, sharpness of the LCR circuit. Now, we try to understand what is this. I am taking one LCR circuit here. Let us say here R equal to 10 ohms and L, let us say 20 millihenry, and capacitor value, let us say 40 microfarad. Think that you have got a one LCR circuit, and this is connected to AC source. Like this. Now, because L is 20 millihenry, C is 40 microfarad, it has got its own resonant frequency. What is the formula for resonant frequency? F naught is equal to 1 divided by 2 pi root LC. So, we can find out the resonant frequency, and the frequency of the AC source is adjusted to the resonant frequency. It is already at resonance. Okay. Now, let us say applied peak voltage. I am not saying that RMS value, applied peak voltage, let us say it is 200 volts. Think that 200 volts. Then already it is at resonance. Therefore, we can find out I naught maximum. I naught maximum is equal to V naught by Z minimum. What is Z minimum? Z minimum is R, that is 10 ohms. So, 200 by 10, that is 10 ampere. Therefore, 20 ampere. Therefore, what is the highest current in the circuit? 20 ampere. I am not talking about RMS value, I am talking about peak value. RMS value bekadre divided by root 2 ಮಾಡಬೇಕು, 20 by root 2. That is the highest RMS value. Okay. Now, we plot the graph. ಇದರದೊಂದು graph ಮಾಡಬೇಕಾಗುತ್ತೆ. We plot the graph of this one. So, I want to plot the graph. Let us say it is the frequency and here it is I naught. Now, we know at resonant frequency current will be maximum, and what is the maximum current? 20 ampere. Let us say that 20 ampere is here. So, that the graph will be like this. It is the resonant frequency. Now, what is the value of R here? 10 ohms. Okay. Now, I am taking another circuit. We take one more circuit. Let us say this R is 100 ohms, L 20 millihenry, and what about C? 40 microfarad. So, what is the change between this circuit and this? Here it is only 10 ohms, here it is 100 ohms, all the remaining values are same. Therefore, even resonant frequency remains same. Resonant frequency of this circuit and this circuit are one and same. Again, we apply peak voltage of 200 volts. Think that. Then already it is at resonance, therefore, I want to find out what is I naught maximum. So, in this case I naught maximum equal to, it is V naught by Z minimum. What is Z minimum? R at resonance. What is V naught? 200 by 100, is it not 2 ampere? So, highest current at resonance is just 2 ampere, and if you plot the graph will be like this. Okay. So, now it is very clear, both the circuits they have got the same resonant frequency, but in the first circuit R is 10 ohm, in the second circuit R is 100 ohms. Therefore, if you look at the graph of variation of current with the frequency, it is like this. In this graph, see here, as you approach the resonant frequency, current sharply increases, and once you cross the resonant frequency, current quickly decreases. There is a lot of change, variation in the current. In this circuit, as you approach the resonant frequency, the current value, it builds up, increases like anything, it goes up to 20 ampere. After that, resonant suddenly decreases almost to low value. But what about in this circuit? Definitely we have got the same type of variation. Other type of variation, but all the variations are very slow. Current slowly increases. What is the highest value? 2 ampere. Then it gradually decreases. Curve is flat. Here curve is steep. Therefore, in this circuit, we have got a good response of current with the frequency. Means current changes by a large value due to the change of frequency in this circuit, not here. Therefore, this circuit has got a higher quality factor and this circuit is a comparatively lower quality factor. It is the comparison. For example, let us say there are two circuits, quality factor of one of them is 60, let us say, and for another one, for one of them quality factor is 60, for another one let us say it is 25. Then immediately we come to know quality factor 60 means you have to recall this graph. In this circuit current sharply increases and curve is more steep, and here it is 25 where graph is almost flattened graph, remember. Current changes with the frequency, but the changes are negligible, difficult to notice, but in this case current rapidly changes when you approach the resonant frequency. So, quality factor tells to what extent current changes with frequency, especially nearer to resonance. Now, somehow we have to calculate that value and we have to express it. Just I said quality factor 60, 25. How we got that value? So, now we think of how to calculate quality factor. It is a derivation. If they ask, they can ask it for 5 marks. But in all the annual exam up to now, they are asking problem on quality factor that I will solve. ಮುಂದೆ ಸಾಲ್ವ್ ಮಾಡಲಿಕ್ಕಿದೆ, ಕ್ವಾಲಿಟಿ ಫ್ಯಾಕ್ಟರ್ ಪ್ರಾಬ್ಲಮ್ ಬರುತ್ತೆ, ಬಟ್ ಡಿರೈವೇಷನ್ ಕೇಳಬಹುದು, 5 ಮಾರ್ಕಿಗೆ ಕೇಳಬಹುದು. ಸೊ ನಾವು ವಿ ಸಿ ದ ಡಿರೈವೇಷನ್. ನೌ ಹೌ ಟು ಕ್ಯಾಲ್ಕುಲೇಟ್ ಕ್ವಾಲಿಟಿ ಫ್ಯಾಕ್ಟರ್, ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಆಫ್ ಕ್ವಾಲಿಟಿ ಫ್ಯಾಕ್ಟರ್. or Q factor or sharpness of the circuit. It is a frequency versus I naught. It need not be I naught, it may be IRMS also. And I said one graph, let us say like this, and another graph what I explained is like this. For both the L-shaped circuit, resonant frequency will be same. Now, what makes the difference? It is the graph we obtained when resistance of the circuit is very low. Therefore, here I will write R value is low, R is a low value. For that graph will be like this, and here R is higher value, high value. Therefore, it is very clear for the high quality factor, resistance of the L-shaped circuit must be very small. Then only the graph will be more steepened and it quickly declines beyond resonant frequency. So, one thing is very clear, if R is small, quality factor is higher. Now, how to calculate, that is the question. Calculation of quality factor. We take only one graph, not both. So, this one is enough. Now, at resonance current will be maximum in my example it is 22 ampere for the first circuit, but generally we write it as it is I naught maximum. Okay. And we know when current is maximum, power consumption is also maximum. Therefore, under resonance current in the circuit is maximum, power consumption is maximum. Therefore, we calculate P maximum is equal to I naught maximum square into R. Now, I will take another particular current somewhere here, which is taken as I naught maximum by root 2. We take another particular current, I naught, this is I naught maximum divided by root, that current we take. Then we draw horizontal line, it is intersecting the graph or curves at 2 points, and we find out corresponding frequencies. Let us say it is F1 and here it is F2. What are F1 and F2? F1 and F2 are the frequencies of the AC for which current in the circuit is I naught maximum by root 2. Now, the question is, what is the speciality of this particular current? For this particular current, power consumption is 50% of the maximum power consumption. That actually we can check it, check ಮಾಡಬಹುದು ಅದನ್ನು. ಹೇಗೆ ಚೆಕ್ ಮಾಡೋದು? Let us say power consumption is P dash for this particular current and only resistor consumes energy, neither the inductor nor the capacitor. Therefore, power consumption is nothing but now I naught maximum by root 2 square of the current into R. I square, what is I now? I naught maximum by root 2, I square into R. Simplify this one. P dash is equal to, it is I naught maximum square R divided by 2. But what is this I naught maximum square into R? Is it not P maximum? Therefore, P dash is equal to P maximum by 2. That means, at resonant frequency, power consumption is maximum. For the frequencies F1 and F2, power consumption is 50% of the maximum power consumption. Think that it is 100 watt maximum power consumption. What is the power consumption here? It is 50 watt, half of that. Hence, F1 and F2 are known as half power frequencies. F1 and F2 are known as what? Half power frequencies. For those two frequencies, power consumption is 50% of the maximum power consumption. Okay. Now, for the further study, to make, we have to derive the formula. To make it simple, instead of F, we take angular frequency. Whether you take omega or frequency, graph everything remains same. What is the relation between omega and F? Omega is equal to 2 pi F. Therefore, here in this x axis every value multiplied by 2 pi. Then x axis changes to omega. If you take it as omega, ಇದನ್ನು ಏನು ಬರಿಬೇಕಾಗುತ್ತೆ? 2 pi into F naught. Is it not omega naught? Yes. 2 pi into F naught, that is omega naught, angular frequency at resonance. Like that, this is written as omega 1 and this is omega 2. What are omega 1 and omega 2? Omega 1 and omega 2 are half power angular frequencies. Omega 1 and omega 2. Half power angular frequencies. Now, this omega 2 minus omega 1, we find out this difference, it is known as bandwidth. Okay. How to calculate bandwidth? Actually, this graph is always symmetric about omega naught. Therefore, we can take this difference as delta omega, and this difference is also delta omega. Therefore, what is the total difference? Total difference is 2 delta omega. 2 delta omega is also equal to omega 2 minus omega 1. And what is this? Bandwidth. Bandwidth of the LCR circuit is equal to 2 delta omega is equal to difference in the half power angular frequencies. Okay. Now, we calculate quality factor. What is the formula for quality factor? Quality factor is calculated as omega naught divided by 2 delta omega. It is the basic equation for quality factor. It is the definition also. So, quality factor is defined as the ratio of angular frequency of LCR circuit at resonance to the band width or difference in half power angular frequencies, which is also equal to omega naught divided by omega 2 minus omega 1, or quality factor is also equal to omega naught L by R. What is omega naught L? Inductive reactance at resonance divided by resistance of the circuit, LCR circuit. And we know omega naught L at resonance is also equal to 1 by omega naught C. Therefore, quality factor is equal to 1 divided by omega naught C R. So, these are the 3 equations for quality factor. Now, from this we derive second equation. This you can expect for 5 marks. This derivation you can expect for 5 marks. Okay. What about unit of quality factor? Look here, it is ratio of the angular frequency to the difference in the angular frequency, radian per second, this is radian per second, they cancel out. Or here this is in ohms, omega naught L, this R is also in ohms. So, it is ohms divided by ohms, they cancel each other. Quality factor is unitless and dimensionless physical quantity.